Hey, this is Andrew Turner coming in with Exponential Functions, KCS at Home, Summer Edition, Part 2. So we've been talking a little bit about exponential functions, and we're going to jump into this with a little bit more context. And so here's a little story about a magician. He's practicing one of his tricks, and part of his trick, he takes a rope, and he's going to cut them in several pieces and magically put them all back together. And so he begins with a 10-foot long rope, and that's very important for filling out this table here. So he has not cut it yet, and that rope is still 10 feet long. So I'm looking for a way to understand how he's cutting it, and he cuts it in half every time he cuts it. So let's say he cuts it that first time, he's now got two that are 5 feet each, or maybe he just discards one side of it. And so that first cut, we're talking about 10 feet long. He cuts it once, he's now at 5 feet long. We think, well, what's half of 5? You cut it twice, you're now at 2.5 feet long. So let's plot that point. And then, you cut it at the third time, you're now at 1.25. And just kind of an estimated point there. Let's say you're at that fourth time, cut that in half, it'd be 75. I don't think that's right, Mr. Turner. Let's see, half of 12 would be 6, so this would be 625. So let's see, 4 to 625, somewhere in there. And then if we were to cut that in half, half of 6 would be 3, and then half of 25 would be 12.5. So you can use a calculator if you would like, just to keep dividing 10 by 2, divide 5 by 2, and so forth, and then we can just estimate these points on the graph. Now, we do not want to connect these because this is not a continuous function. At no point is there a 0.1 cut that results in 19 feet or anything like that. These are what we call discrete points after we have cut it in, integer cuts. There's no infinite possible decimal ways that you can begin exploring that graph in a continuous way. So let's talk a little bit about growth and decay. And if you're looking at that other one, you may think, well, was it growing or was it decaying? And we can kind of see as that graph is shifting down from left to right, cutting that rope in half so it was decaying. So let's look at some context that may do more with population. When you're talking about population of towns, really thinking a lot about your geometric model. You have your first value, you have your common ratio, what you're multiplying by over and over and over, and then you have your exponent. Well, for population questions, we have what's called the principal value, and then we have our common percent ratio, or our percentage rate of increase or decrease, and then we're raising it to our time. So a lot of similarities between these formulas. You have a starting multiplier, there's something in parentheses that you're going to have as your ratio, and then you have some exponent value on the parentheses. So let's think about our population of downtown. You're starting with 20,000 as your initial population, principal value, y-intercept. And then it says that people are moving away from downtown, so I want to use the subtraction for decay. And then this percentage rate of 1.5%, I want to use that value as a decimal. So divide that by 100, and that would be 0.015 raised to the t. Using the second equation, it says that their population started at 6,000. And it was actually growing at a rate of 1.8%. And so we want to, again, divide that by 100, and that is 0.018. Kind of hard to read there. And then you want the time. So I thought I would use a graphing calculator here to basically get us a graph going. So I have typed it into our equation editor. We're going to go 0 to 22, going by 2s for the x-axis at the bottom. And for the y-axis, I want to go 0 to, let's see, that would have been maybe 42,000, something like that. And we're going to go in units of 4,000. Okay, so that's just going to kind of give us a quick little curve, and it's more like this exponential curve here, but we're kind of zoomed in really closely on a particular portion that's in the first quadrant only, this area of the graph. And so we're going to get a few points using input, output. In that initial year, when you plug in 0, you're getting 20,000. When you plug in 2, you're getting about 19,400. Let's see if we can estimate that. It's going to be really close to the 20,000. And let's see, after 6 years, you're at 18,266. So maybe somewhere in here, guess estimate. Let's see, 10 gives you 17,000. And then let's plug in 14. You're going to see these output values continuing to move down further and further and further because the population of the town is decreasing. In 18 years, it's down to 15.2. So you may think, it's not really moving that fast. And you're correct, but basically it is continuing to decrease over time by a rate of 1.5%. So let's try to see what the other graph would look like using a similar scale. Let's do 6,000. Let's add, and let's make it 1.8%. And then I think I want to keep my time scale, but for my Y min and max, I'm not going quite as high. It looks like I go just to about 10,000 for this one. So let's change that to 10,000. And I think my scale for this was going by 1,000s just for the second graph. So we'll notice that this one is scaling up a little bit. Initially, you're at 6,000, but after 2 years, you're just up a little bit. 1.8% is not that much. So you start at 6,000, and you're just a little bit above that. And then a few more years later, you're at 66. And it almost feels linear at first, but as you really study these numbers, they're not going up linearly at all. They are slowly getting a little bit steeper, over and over, a little bit steeper, until it's just curving up, 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 up. Probably not that quite drastic for the points that I've got coming. Let's just see what happens when you plug in 22, that end point, 88, 83. So that's going to be somewhere around here. So it's just going to keep on tracking somewhere like that. Okay, so we can just keep on plugging in other points to find other situations. So really want to just make sure you understand a little bit about that y-intercept value. That's where your graph is starting, 6,000. Or for this one, you're starting at 20,000. What made the first one go down over time is the fact that you were decreasing. We used a value less than 1. We subtracted there. Versus in the second one, we're going up over time, increasing, and we're using a value that is greater than 1 because we added to that particular value. So let's try another one like that. Scientists researching bacteria found recently in animal cages at a zoo starts with 200. So there's our p-value or your A1 value if you're thinking about it with sequences. And then we got to really jump in there and see, well, are we increasing or decreasing and by what percent? So let's see, we start with 200. We have 1. Are we doing plus or minus? He determines every hour that it's increasing by 25%. So let's use the plus. And if you divide 25% by 100, that is 0.25 as a decimal. So we're going to sketch a picture of this bacteria model by saying, okay, well, if we start with 200, that's our first point way down here, right there at 0, 200. And maybe we'll use the calculator again to get some good input-output points. Let's see, we had 200. Let's just clear all that. 200. We were doing 1 plus 25% as a decimal. And then we are raising that to different powers or different years. So we can see that this is really increasing rapidly. And it's because 25%, that's a pretty big percentage, way more than 1% or 1.5%. So we're increasing much, much quicker. And so let's see, when we plug in 1, we should be at 250. So 1 gives you somewhere in here 250. And, you know, I don't have to plug in every point. Let's plug in 3. Gives you about 390. Okay, so that's really pushing close to 400. Let's see what happens when you get to 6. 762. So that's somewhere about here, maybe. Let's see. 9 would produce 1490. Somewhere there. A few more points. You know, we don't have to plug in every single point, but a few more will really make it round off well. 2910, if I remember it. 2910. Somewhere up here. And so, because this is a continuous bacteria growth, we can connect all these points because even in between times, you know, 1.2 years or 2.3 weeks, just the bacteria has been growing continuously, so we do want a continuous graph when we connect all of those together. So it says, then estimate the number of bacteria that the scientists should let the bacteria grow to have no more than 2,000. So I want to consider maybe graphing a constant. Let's just graph 2,000, no variable, and let that kind of show us where exactly 2,000 is on the y-axis. And let's try to find exactly what we think that input would be to make roughly 2,000. So it looks like 11 makes 2,300. You know, 10, that's a little low. You know, 10.5. Okay, I'm a little high now. 10.4. 10.3, you know, really getting close. I want this to be as close to 2,000 as possible. And so when we talked about a system of equations in the previous chapters, we can do second trace and ask the calculator to find that exact point of intersection, and it'll tell us exactly the number that makes that exactly 2,000. So it looks like 10.318. This is the amount of years it's going to take, or weeks, depends on the problem. Looks like hours, number of hours to get exactly 2,000. So if you had 10.30, I can't remember exactly what it was. We'll look back. 3188 maybe. Or maybe we'll say 3189 hours. That would be exactly 2,000 bacteria. And again, we just found that by graphing a constant, 2,000, and then really finding exactly where we think that point of intersection would be, what the x value would be to make that happen. So you can see that's somewhere around 10, 11. Okay. That pretty much wraps up our exponential chapter. We got one more unit on polynomials. Hope to see you then.